We're going to look here at finding a lower bound to the travelling salesman problem using the deleted vertex algorithm. So here we have a copy of a graph, and we're asked to find a lower bound by deleting vertex A. You can repeat this process by deleting different vertices. So if we delete vertex A, we remove every edge that is incident to A. So we're then going to find the minimum spanning tree of the remaining graph, B, C, D, E, F. So to find a minimum spanning tree, we're going to initially take the lowest edge on there, BC. It's 4. And then we're going to continue to add edges, the lowest edge possible that is incident to the existing tree, so it touches the existing tree and it doesn't form a loop at all, doesn't visit a point we've already visited. So in this case, the only options are CD or BD to add, and clearly BD is lower, so we add that value. Then we look at what's left of add, and DE is our next lowest at 7, and then EF at 8. So that gives us a minimum spanning tree. Finally though, we need to connect that minimum spanning tree back to the point A. We need to connect it twice so that we can leave from A and return to A, because we know that that was the point of our algorithm. So we pick the two lowest values, in this case A to E and A to B. And that leaves us with a lower bound of just adding together all of those things. 5 plus 4 plus 4 plus 6 plus 7 plus 8. I believe it gives us 34 as a lower bound. Now, we'll look at proving later why this is always a lower bound. But in this case here, you can see that it is a lower bound because it connects all the points up. But actually, if we wanted to start and finish at A, for example, there'd be no way we could follow this route without doubling back at some point. So I started at A, I would go to E, I'd have to go to F and back, or carry on around. There's no way that I could complete this. And so the actual route I would have to take if I was using this would be longer. So therefore this is a lower bound. And we'll look at proving that this is always a lower bound later on. This same problem can be considered using a table of least distances. So often you'll be given that rather than a graph. But here I've turned the graph into a table of least distances. We're still asked to begin by removing vertex A. And then we're going to apply Prim's algorithm to the remaining table. So first thing we do is pick the lowest value, which is this 4, that isn't a 0, and we remove columns B and C because that connects points B and C. Available to us, B and C, and so we pick the lowest value that is incident to the tree, so that is in B and C that we've got left, so that is D. Cross out the rest of the column, and again we can choose from any of these 3 rows, so we pick the next lowest value, which is the 7 in E, and so we cross out E. We can now pick the lowest value from any of these, which is going to be the 8, taking us to F, by which point we have completed the minimum spanning tree. Remember, we must connect back to point A, so we pick the 2 lowest values that connect A to any other points. And we get the same calculation we did before, that the lower bound is made up of 5 plus 4 plus 6 plus 4 plus 7 plus 8, which is 34. In order to prove why the deleted vertex algorithm gives us a lower bound, it's worth considering the actual solution to the travelling salesman problem in this case. So this is done by trying all of the possible routes, and you can see on the right hand side with the purple line the actual solution to the travelling salesman problem in this case, which has a weight of 39, and our solution from earlier, which gave us a lower bound of 34. So for a starter, the weight is greater. That's a good sign. So we need to think about what if this is a lower bound. We know that it's the lowest possible solution. Now we know this didn't actually work as a solution because we couldn't follow this route directly. So therefore, to make it a possible route, we'd have to duplicate some sides, and the actual result would be bigger at least. So what we do is, if we want to show this as a lower bound, we must prove that what's on the right hand side must be greater than or equal to what's on the left hand side. We're going to do this by considering the two parts. So in this case, we deleted A. We deleted A, and the first bit was to find the minimum spanning tree. Now, if we consider on the right hand side deleting A, we would lose AB and AF, and we'd be left with the root that I'm highlighting now in red. Now that is a spanning tree of B, C, D, E and F, which is what we had here, B, C, D, E and F. However, we know that the left-hand side is the minimum spanning tree. So what's on the right-hand side must be, well, we could have ended up with the minimum spanning tree, so it could be equal, but it must be equal or greater. And in this case here, we can see that that's going to be greater than the minimum spanning tree. So what's on the right-hand side must be bigger for that bit there. The second part we looked at was the bit connecting A back to the graph. And so here we said on the minimum, on the lower bound, we connected using these two. We chose the lowest two of the available edges. Therefore, when we look at this one, we can see that we actually didn't choose the lowest two. So again, it must be greater. And it could be equal. We could have taken the other route, but as it was, that didn't work for this minimum route. But at worst, it can be equal, and it must be bigger. So both parts could be equal or must be greater. They could neither the red part nor the blue part could be less on the right-hand side than the left-hand side, which means, as a result of this, that what we end up with is an upper bound. What we end up with is a lower bound on the left-hand side and a value on the right-hand side, which, if we got it exactly right, could be the same, but must be the same or greater. Hence, we have a lower bound on the left-hand side.